This is the 6th video in a series devoted to a course in abstract algebra. And in the previous couple of videos, I think in the previous 3 videos, we looked at examples of groups. Well, that was of course after defining what a group was. So we looked at some basic examples like the integers with addition, the real numbers with addition, non-zero real numbers with multiplication, some matrix groups, groups of units. We also looked at dihedral groups and permutation groups. So at this point, we've got a fairly large catalog of examples of groups to work with, which means we're in a great position to start proving general results about groups. And so after proving those general results about groups, it may be necessary to build intuition by looking at some examples of groups, but now we've got lots of examples, so that's good. Now, before we get into some of our first results of the day, I'd like to recall the precise definition of a group again. So a group is a set G together with a binary operation. So it takes 2 inputs from G and gives us an output from G. And it satisfies 3 axioms. I've left off the closure axiom, which we had before, because that's built into the structure of this binary operation. So first off, we must have an identity. So in other words, there's an element which is generally called E in G, such that GE equals EG, which equals G. And that is for all little g in G. So in other words, combining things with the identity does not change whatever you're starting with. Then next, everything must have an inverse. So for every little g in G, there is an element little g inverse in G, so that when you combine G with G inverse in either order, you get back to the identity. So it's any element's path back to the identity. Next up, we have associativity, and that says for all x, y, z in G, x times yz is the same thing as x times y times z. And then notice we do not have commutativity here, and we saw lots of examples of non-commutative groups. But let's recall that if a group is commutative, then it's called abelian. And furthermore, if we're working with a specific group where the operation is addition or maybe something other than multiplication, we might write that operation. Okay, so let's look at our first suite of examples or maybe results for general groups. So let's suppose G is a group. We'll start off by proving that the identity is unique. Okay, so let's get to it. So let's maybe suppose that E1 and E2 in G are both identity elements. So they're both identities. And what we'd like to do is show that they must be equal to each other. So we have E1 has got to be the same thing as E1 times E2. This equality is true because E2 is an identity. So combining E2 with anything doesn't leave that thing changed. Okay, but now you can maybe see where we're going. This is the same thing as E2, and this equality is because E1 is an identity. So combining anything with E1 leaves it unchanged. But let's see what we have. We started with 2 possible identities and we showed they had to be the same. So that means there is only, in fact, 1 identity. Okay, great. So that proves this first result. Okay, so next up, let's maybe prove that inverses are unique, which is this second claim. And we'll do that in a similar strategy. So let's take what I'll call little g in G and suppose that little a and little b in G are both inverses of little g. And what we'd like to do is show that A is equal to B, which really motivates the ability to use this notation G inverse here. This notation doesn't make a ton of sense if inverses are not unique, because this inverse notation would give you more than one element. Okay, so let's maybe get to it. So since A and B are both inverses of G, we have two facts. We have AG is the same thing as GA, which is equal to the identity. Okay, and we also have BG is the same thing as GB, which is the identity. So we've got something like that. Okay, so now how can we put these two things together? Well, maybe the way I'll do it is like this. Let's start over here with A, and let's notice that A is the same thing as A times the identity. But let's use a version of the identity that we have on the board. Maybe we'll use this version of the identity, G times B. So that allows us to write this as A times G times B. But now we have associativity to write this as AG times B. But notice that AG is equal to the identity because of our inverse relationship. So this is equal to the identity times B, which is equal to B. So let's notice this string of equations tells us that A is equal to B. So that means that we have A is B, which is equal to G inverse, really inspiring that use of the notation. Okay, so now let's look at this next one that says for every A and B in G, there is a unique X such that AX equals B. Okay. So let's maybe show existence first, and then we'll show uniqueness. And existence is pretty easy. So let's note if AX is equal to B, then we can left multiply by both sides to get X is equal to A inverse times B. So I guess I should have said there that we are left multiplying by A inverse, and that's always possible because we're in a group. Now let's notice if we plug that value of X into our original equation is definitely satisfied. So we've got A times A inverse B is equal to, well, we can reassociate there to cancel out the A and the A inverse, but that gives us B as needed. So now let's prove that this X is indeed unique. So let's suppose X and Y are in the group such that AX equals B and AY equals B. But look, that means that in fact AX is equal to AY, and then left multiplying by A inverse will give us X equals Y. But that's exactly where we needed to end up. So that means we've proven this result right here. And actually in this last step from here to here, where I said it in words but I didn't write it, I multiplied on the left by A inverse. We have indeed proven this result right here. So if AB equals AC, then B equals C. That's exactly encoded into this over here. Here you simply left multiply by A inverse. And likewise, over here, if XY is equal to ZY, then X is equal to Z. That's by right multiplying by Y inverse. So I won't write those out. I think those are fairly simple. So there's our first suite of results involving general groups. Let's prove a couple more. So here's 3 more basic results about general groups. So the first says that for elements A and B inside the group, the inverse of A times B is equal to the inverse of B times the inverse of A. So notice it switches the order, if you will. So this should maybe be familiar from linear algebra when you're learning about inverses of matrices. Also, this is sometimes called the shoes and socks theorem. And that's because in order to put shoes on, you must first put your socks on and then put your shoes on. Whereas to take them off, you first take your shoes off and then your socks off. So you reverse the order there. Okay, so let's prove this real quick. So this is actually, surprisingly fast because we'll use the fact that we have uniqueness of inverses. So let's notice that A times B inverse times A inverse reassociating gives us A times B inverse times A inverse, which gives us A times the identity, this term right here, but I'll just leave that off, times A inverse, which is indeed equal to the identity. But let's see what we can do from there. We can do a couple of things. We can notice that this equation tells us that the inverse of AB is B inverse A inverse, and since inverses are unique, we know those are equal to each other. Or we could left multiply by AB quantity inverse. And maybe if we were to do it that way, we would just get all the way to the end. So we have AB quantity inverse is B inverse A inverse as needed. Okay, good. So we've proven this first result. The next result will prove that if A times B quantity squared equals A squared times B squared, then AB is in fact equal to BA. So in other words, if we have this condition on those two elements, then those two elements commute, which in general they don't, as we've seen with a bunch of examples of groups already. Okay, so how might we do this? Well, let's start with this right here. We have A squared times B squared on the one hand is equal to AB quantity squared by our given. But that's also equal to A times B, and then I'll associate it so that I have the A times B in the middle like that. Okay, so that's looking good. But now we can multiply this out to give us A times B times A times B, and then I'll associate it to have the B times A in the middle like that. Then we will left multiply by A inverse, and that's going to give us A times B is equal to B times A times B. And then finally, we will right multiply by B inverse, and that'll give us the result. We'll have AB is equal to BA. Likewise, since we have cancellation rules that we proved on the last board, we could simply left cancel the A and right cancel the B to have the result immediately. So now after looking at this proof, I often like to streamline these things so that you have a single equation starting with AB and then ending at BA. So this doesn't create something more correct or less correct. I just like the aesthetics of having that sort of sequence of events. So in other words, starting with AB, ending with BA, using this fact over here. So let's see how we might do this. And this is not something that is a requirement for writing these things down, but I think it's a nice game to play to get used to or to practice like these kind of group operation problems. Okay, so let's start with A times B. And let's notice we'd like to build something like A squared B squared. And I can do that by left multiplying by the identity and also right multiplying by the identity. But I'll choose the correct version of the identity. So I'll multiply by A inverse times A times AB. So there, I left multiplied by that version of the identity, and I'll right multiply by B inverse. So that's another version of the identity. Okay, so that's looking good. But now I'm going to reassociate. That'll give me A inverse, and then we'll have A squared B squared, and then we'll have B inverse. So something like that. But then I can rewrite that as A inverse times AB squared times B inverse using my given. But then finally, that's equal to A inverse A equal to A inverse AB times B inverse. Just given the expansion of A times B quantity squared. But now this A inverse and this A cancel, and this B inverse and this B cancel, leaving us with B times A. So now that we've got this nice string of equalities that start with AB and end with BA. And let's see, at this stage right here, we used the given statement. So like I said before, this is not a requirement. I just kind of like things written like this. But that's just personal preference. I think other people would probably prefer something like this one up here. Okay, so but either way you have it, we have proven this result. And now let's move on to the third. So for our final basic result, before we move on and talk about something called subgroups, we will prove that if the order of little g is equal to 2 for all little g in big G, then G is indeed abelian. Okay, so let's maybe recall that the order of little g being equal to 2 tells us that G squared is equal to the identity, and this is true for all g in G in this case. And what we'd like to do is take little a and little b inside the group and show that they commute. So here, let's put that here. So we want to show that little a b is equal to little b a, using, like I said, this fact right here. So the most obvious thing to do is to take little a times b and square it. We know that we get to the identity. So let's do that. So let's notice that the identity is equal to little a times little b squared. In turn, that's equal to a times b times a times b. But now what we'll do is left multiply by a and right multiply by b. So there, left multiply by a, and then we will, like I said, right multiply by b. So let's see, that's going to end up with a times b on the left-hand side, and then on the right-hand side, we'll have a squared times ba times b squared. But since the order of everything is 2, a squared and b squared are both the identity, so this simply leaves us with b times a. Now, let's see, we could do this a couple of different ways, and let's sketch those. So one way is we could say, let's note that since everything squares to the identity, everything is its own inverse. So in other words, G is equal to G inverse. But that means that AB inverse is equal to AB, but also this is equal to B inverse A inverse by our previous result. But then B inverse is equal to B and A inverse is equal to A, so we get the result immediately like that. Of course, that's using this result up here. Then we could also write this in like one string of equations, kind of motivated by what we saw right here. So let's see maybe how that would work. So let's notice that A times B, and now we'll open up the space between A and B and multiply by the identity. But we'll multiply by the identity in the form of AB quantity squared. So in other words, we have A and then AB squared and then B. But now let's expand that out. That expands out to A times B times A times B times B. So there's our AB squared. But check it out. This is A times A, which is A squared. That's the identity. This is B times B, which is B squared. That's the identity. So in the end, we get the identity times B times A times the identity, so we get B times A. So there's another way of writing this. Okay, so now let's look at the notion of a subgroup. So given a group G and a subset H of G, we say that H is a subgroup, and we'll use the following notation. So I would read this as the H is a subgroup of G, but this is like an angular set inclusion, or like a less than or equal to sign. Okay, so back to it. H is a subgroup of G if it contains the identity, so it's got to contain the identity. If little h is in H, H inverse is in H, so it contains all of its inverses, and then it is also closed under the operation. So for AB in H, A times B is in H. I'd like to point out that there's no talk of associativity here, and that's because the associativity of the operation is inherited from the structure on G. Okay, so let's look at some examples. So let's maybe start with the group Z and look at some subgroups of G. Well, let's notice that the subgroup just containing the identity element 0 is a subgroup of G. So this is not super interesting, but it definitely satisfies all of these rules. And that's because the inverse of 0 is equal to 0, and 0 plus 0 is equal to 0. And 0 is the identity. So it's closed under taking inverses and under the operation. Okay, so now let's look at maybe a little bit more interesting subgroup of Z, maybe this. So -4, -2, 0, 2, 4, dot, dot, dot. And that's happening in both directions. So this is the set of all even integers. And there's some notation for that, and that is 2Z. And this is most definitely a subgroup of Z as well. And that's because if you have two even integers and you add them, then you get the output of an even integer. So you probably proved something like that in an intro to proofs class. Furthermore, 0 is an even number, so it contains the identity. And any even number has a negative, which is also an even number, so we're good to go there as well. Okay, so let's maybe look at some other examples. Let's note that we actually have this nice string of subgroup relationships starting at Z. Notice that Z with addition is a subgroup of the rational numbers with addition, which is a subgroup of the real numbers, which is a subgroup of the complex numbers with addition. And we could have the same sort of thing with multiplication. So notice we could take the subgroup of everything of the order 2 to the n, where n is an integer. So this would be like a half, 1, 2, 4, we've got a quarter, we've got an eighth, so on and so forth. So this is all powers of 2. This is closed under multiplication, and it's a group under multiplication. That's pretty easy to check. We won't check that here. So let's notice that that is a subgroup of the multiplicative group of non-zero rational numbers, which we looked at before, which is in turn a subgroup of the group of non-zero real numbers. We looked at that group before, which is in turn a subgroup of the group of non-zero complex numbers. Okay, well, let's look at some others. So let's maybe look at this one. So I think this is a good one. Let's say our group is Z9. And then we have a couple of different things that we can do inside of Z9. So notice that the group containing 0, 3, and 6 is a subgroup of Z9. It contains the identity. It contains all inverses. Notice that 3 plus 6 is equal to 9, which is equal to 0 inside of Z9. And it's closed. So actually, this shows that it's closed. And then I guess maybe the only other interesting subgroup here would be just the set containing 0. So that's also definitely a subgroup of Z9. Now here's one more interesting example, and let's consider a square for a minute. And let's maybe label the vertices of the square 1, 2, 3, 4. And let's notice that rotation by 90 degrees is like the permutation that sends 1 to 2, 2 to 3, and 3 to 4. And reflection about this axis right here is the same thing as the permutation that sends 1 to 2 and 3 to 4 like that. But notice that that's exactly what's going on with the dihedral group. It's just putting the dihedral group in terms of things that are inside of the permutation group S4. So what this does is it puts a copy of D4 inside of S4. And we'll maybe talk about what I really mean by a copy of D4 later, but I'll let you just think about that at the moment. Okay, so now that we've looked at some examples, let's look at a nice test for showing things are subgroups. Now we're going to prove something called the subgroup test, or sometimes the one-step subgroup test, because you can prove these three things all at once. And I'd like to point out that anytime you've got some sort of setup and you want to prove that something is a subgroup, maybe go to this test. This is like a great first place to start for proving something is a subgroup. Okay, so let's see what it says. Let's suppose that G is a group and H is a subset of G which is non-empty. Then H is a subgroup of G if and only if for all A and B in H, A, B inverse is in H. Okay, so let's prove this. Which direction should we do first? Maybe the forward direction. So that means we want to suppose that H is a subgroup of G, and notice that if A and B are in H, then we know that B inverse is in H because H is a subgroup, but then that tells us that A, B inverse is in H, you know, by this rule right here applied to B being replaced with B inverse. But that's exactly what we needed to do to prove this forward direction. And in fact, this forward direction is not like super helpful because it doesn't give us a shortcut. The reverse direction is what gives us a shortcut. Okay, so let's do that reverse direction. So let's suppose that for all A and B in H, we have A, B inverse in H. And then what we want to do is show that we have a subgroup. But to show that we have a subgroup, there are three things that we need. We need the identity, then we need inverses, and then we need this right here. So let's start with the identity. So let's apply the rule up here to the case where A is equal to B. Okay, but that tells us that we know E, which is equal to A times A inverse, is inside of H. So we've got E is inside of H. We're good to go. So now let's move on to this next bit with inverses. And you might guess that we're just going to apply this rule again. So let's apply this rule again with A is equal to the identity, which is allowed because we've already shown that the identity is inside the set, and B is equal to our element of H. Okay, so that's going to give us H inverse, which is equal to E times H inverse, is inside of H. So in other words, we have inverses. So now let's finish this off by proving that we are closed under the operation. And one more time, we're going to apply our rule. So in this case, let's apply our rule with A is equal to A and B is equal to B inverse. So I'll put that in quotes. So what does that tell us? So that tells us that A times B is equal to A times B inverse, which is inside of H. Notice we know that B inverse is inside of H by this rule up here. So now we have closure. But these three things put together tells us that we indeed have a subgroup, and that finishes the proof of this subgroup test. Now we're going to informally look at something called a subgroup lattice. This is a nice way of getting a picture of the subgroups of a group. Okay, so let's start with some groups of order 4. Now, as we'll see later, there are exactly two groups of order 4. There is Z4, and then there is Z2 cross Z2. So Z4 contains 0, 1, 2, and 3. Recall that we're working mod 4 in this case. And Z2 cross Z2 involves the ordered pairs 0, 0, 1, 0, 0, 1, and 1, 1. Where in each of those entries in the ordered pairs we're working modulo 2. Okay, well, Z4 in fact only has one subgroup, and that is the subgroup containing just 0 and 2. You can easily check that that is a subgroup. Notice it contains the identity, and the only non-identity element is its own inverse, so it contains inverses as well. Now, I'd like to give some notation here. We might say that this is equal to the group which is angle brackets 2. And that's the group generated by 2. What I mean by that is that that's all combinations of 2 with itself until we close everything up. Notice that we've got 2 in there, and then 2 combined with itself. 2 plus 2 is 4, but in Z4 that's equal to 0. And that ends everything. Then we've got another subgroup which is kind of interesting, and which is kind of boring, and that's the trivial subgroup, which is just 0. Since we're working in an additive group here, we would generally denote that as just the subgroup 0. Now let's go over here and look at Z2 cross Z2. So there are two subgroups of order 2 that jump out immediately. One would be Z2 cross 0. So which one would that be? Well, maybe let's put that in a box here, and that would be the subgroup containing this element and this element. Great. So in other words, the second component is always 0. And then likewise, there's a subgroup that looks like 0 cross Z2, and that would be the subgroup containing this element and this element. So the first element is always 0. And then there's one other subgroup of order 2, and that would be the subgroup containing 0, 0, and 1, 1. So that would be the subgroup, well, containing those two elements. Can't be really written in terms of the component groups very well. Sometimes called the diagonal subgroup, if you will. And then there's a subgroup of all of these, which is the subgroup containing the ordered pair 0, 0. And recall that we notated that as 0 before. So I won't prove this, but those are complete subgroup lattices of all groups of order 4. Now let's move on to groups of order 6. Okay, so now we're going to make a subgroup lattice for the two groups of order 6. So I'll just say again, there are two groups of order 6. We're not going to prove that just now. That's something that we'll prove later. So let's start with Z6. Let's recall that that's the numbers 1, 2, 3, 4, 5, where we take our addition modulo 6. It's really equivalence classes modulo 6. Okay. So we have a subgroup of order 3, in other words, a 3-element subgroup, which looks like 0, 2, 4. Let's notice that that is the subgroup generated by the number 2. And then there's also a subgroup of order 2, which is the group or the subgroup containing 0 and 3. That's the subgroup generated by 3. And then down here we have the 0 subgroup. So we've got some sort of picture like this. Now I'd like to point out that this subgroup of order 3 is above the subgroup of order 2, and that's a standard thing to do when we're making these subgroup lattices, is to put them in some sort of hierarchy like this. And now let's look at D3. Recall that that is the dihedral group of order 6. In other words, it is the group of symmetries of an equilateral triangle. Okay, so let's recall that that contained elements E, R, R squared, S, SR, and SR squared. The first 3 were rotations, whereas the last 3 were reflections. Okay, so let's notice that here we've got a subgroup of order 3, which is simply the rotations. So this is ERR squared. You might notice that this is generated by little r. Also, this is sometimes called C3 for the group of rotations. We'll investigate those kind of things a little bit later more. And then you've got a couple of, or actually 3 subgroups of order 2 made by the reflections. So let's recall that all of these reflections are order 2 elements, which means they are their own inverse, which gives you a pretty easy way to make subgroups out of them. You've got this one right here, which contains E and S. You've got this one next to it, which contains E and SR. And then finally one next to it, which is E and SR squared. So those are your three subgroups of reflections. And then down here, you've got the identity subgroup. But since our operation is more akin to multiplication in this case, we might call it 1 instead of 0. Okay, so this actually highlights a nice difference between D3, a group of order 6, and Z6, a group of order 6, in that their subgroup lattices are different. Now we're going to look at a couple of general subgroups of general groups. So let's say we've got a group G and a subset, not a subgroup, or not necessarily a subgroup, S of G. Sometimes this is in fact a singleton. In fact, in most of the examples we'll look at today, this is a singleton. So the centralizer of S in G, which we denote by CGS, is all group elements G such that GS equals SG for everything in S. So in other words, it is elements of G that commute with all of the elements of S. And then off of that, we can define something called the center of G, which is in fact just equal to CGG. So that's everything that commutes with everything else in the group. And that's what we have here. So let's prove the following results. And that is that all three of these are indeed subgroups. And I'd like to point out that they're all non-empty immediately, and that's because they all contain the identity. And that's in fact because the identity commutes with everything. So notice putting the identity here just leaves you with S, and S is in S. I forgot here that this is for all S in S. And then of course, like, the identity commutes with everything here and it commutes with everything here. So we're good to go. Anyway, all of these contain the identity. So let's start by proving that CGS is indeed a subgroup, and we'll use the subgroup test. So let's suppose that little a and little b are in the centralizer NG of S. So let's recall real quick what that means in terms of our definition. It's good to keep this in mind. This means that A times S is equal to S times A, and B times S is equal to S times B, and this is true for all S in S. Okay, and then where do we want to go? Well, it's probably useful to point that out as well. So what we'd like to show is that little a times little b inverse times S is the same thing as S times little a times little b inverse. And why would we want to do that? Because that'll tell us that little a b inverse is in this centralizer. Remember that being commutative with everything from S is the entry fee to be inside of this centralizer. So that's why we'd want to do this. Okay, so let's get to it. So let's maybe note that since B times S is the same thing as S times B, we can left multiply, so let's maybe put left multiply by B inverse, and we'll right multiply also by B inverse, and that's going to end up giving us S B inverse equals B inverse S. So that's cool, we kind of cancel things out as needed. But notice this immediately tells us that B inverse is in this centralizer. Okay, so that's good. Now let's maybe go right to this goal right here and see if we can work it out. So we've got A times B inverse times S. So let's reassociate to have this be A times B inverse times S. But then since B inverse is in the centralizer, we can slide it past S. That gives us A times S times B inverse. Again, that's because B inverse is in the centralizer, which we just showed. But then reassociating, that gives us A times S times B inverse. But then since A is in the centralizer, we can pass it past S. So that gives us S times A times B inverse. And then reassociating gives us S times AB inverse. But check it out. This extreme left and right hand side is exactly what we need to have A, B inverse in the centralizer of S, which means by the subgroup test we're good to go. We have proven that this is indeed a subgroup. But notice that since the center is a special case of the centralizer, that immediately tells us that the center is also a subgroup of the group. So we know the centralizer is a subgroup and the center is a subgroup. Let's maybe check those off. So check here and check here. Now I'd like to look at an example of some centralizers in D4. So let's notice that the centralizer in D4 of the singleton containing the identity, which I'll just like drop off the singleton of the set thing here and just put the identity. So by our definition over here, that'll be everything that commutes with the identity. But let's notice that everything commutes with the identity, just by definition. So this is in fact equal to the entire group. But also R squared commutes with everything, so this is also the centralizer in D4 of R squared. And notice that is because R squared times S is the same thing as S times R to the 4 minus 2, which is R squared again. It commutes with S, but it commutes with the other generator R, so we're good to go there as well. Okay, so now let's look at C D4 of the element R. So this should be everything that commutes with R. So none of the reflections commute with R. You can easily check that RS is equal to SR cubed, as we did in a previous video. The only thing that commutes with R is the rotations. So ER, R squared, and R cubed, but that's also the centralizer in D4 of R cubed. Okay, nice. Now let's look at the centralizer in D4 of S. So that'll contain the identity, it'll contain S itself, it'll contain R squared, and it'll contain SR squared. It'll contain those 4 elements. And indeed, this is the same thing as the centralizer in D4 of SR squared. Now let's look at the centralizer in D4 of SR. So what commutes with SR? Well, we'll have the identity, we'll have SR, and we'll have R squared. So anything commutes with itself, and R squared commutes with everything. And then we'll have the combination of these two, which is SR cubed. Then you can check everything else does not commute with SR. But notice this is also the centralizer in D4 of SR cubed. And then finally, we'd probably like to know the center of D4 as well. And you can check that the only thing that commutes with everything is the identity and R squared. So that's the center of D4. Now I'll leave you with some warm-ups. 3 warm-up exercises based on what we did today. The first, let's suppose that we've got a group G and an element little g, where G to the 10 is equal to the identity, but G squared is not the identity. And then what we'd like to do is show that G cubed is also not the identity, and G to the 8th is also not the identity. Then let's find the order of little g. Next, let's make subgroup lattices for S3 and Z8. And if you're in my class, we'll also make subgroup lattices for Z4 cross Z2 and D4 in class. If you want to add those to this warm-up if you're not in my class, that'd probably be a good exercise. Finally, let's find the centralizer in D6 of the element SR, the center of D6, and the centralizer in S4 of the permutation 1, 2. And that's a good place to stop.